So these first 3 lectures, we've really just given the fundamental definitions of dynamical systems, like discrete time, continuous time, differential equations as generators of continuous time dynamical systems. So now we start the core, in some sense, of the course, and the fun part, which is attempt to give a classification of dynamical systems. Right? Otherwise, there's just too many dynamical systems. Right? If you just take as an example the linear maps, this family of maps, of linear maps. Remember we looked at these, where x goes to lambda x. If you remember, we had all different cases depending on the values of lambda. Right? So this is a lot of dynamical systems. Here we have the real line, 0, and then depending on lambda we have different dynamics. So is there some natural way in which we can think of two maps, two dynamical systems belonging to this family as being equivalent in some way, as being the same map? This is the question, right? So, for example, suppose you take lambda equals -5 and lambda equals 1/2. What is the difference in the dynamics here? That's right. So would we kind of think of them as equivalent in some way or different? Different. Why? The dynamics is different because in one case it's attracting towards 0, in another case it's repelling towards 0. Okay, so what if we take lambda equals 1/2 and lambda equals 1/3? Would we consider these to be equivalent? Yeah? Because they're all attracting towards 0. What if we take lambda equals 1/3 and lambda equals -1/2?
No, because it flips.
Because it flips. So we won't really want to consider them as equivalent. But how do we formalize this idea in general?
That they have the same attracting point and repelling point?
That's a start. We can say, okay, if a dynamical system has an attracting fixed point, another dynamical system which is equivalent to this one should at least also have an attracting fixed point. Otherwise, it doesn't make sense to think of them as the same. Maybe we could also say if they have, if one system has a periodic orbit of period 5, then the other system should also have a periodic orbit of period 5. So they should at least have the same set of periodic orbits, perhaps. You know, we're trying to give a criteria by which we say two dynamical systems are different in some sense. If they don't at least have the same set of periodic orbits, then okay, one of them is missing this, then they're not really the same. Okay. What about non-periodic orbits? You know, we looked at circular rotations, remember? If the circular rotation is irrational, then it doesn't have any periodic orbits. So if two circular rotations are irrational, are they equivalent to each other? In other words, how do we really need to match up the dynamics?
Yes, transform them into the other.
Because both of them has a dense subset, and this dense subset is countable. It should be that the limiting case, both of them should be the same. So we should consider them as having the same dynamics.
I don't know. This is why we need, the reason why I'm giving you all these examples is to point out that we need some kind of definition, right, in math. Not just an intuition. I mean, there's a kind of intuition that some characteristics are easy, like certainly if you have the same set of periodic points, then they are possibly equivalent. But there's also the question of the non-periodic orbits. You know, what really do we consider as being the same, right? So let me give here the general definition. Let us suppose that we have one dynamical system F on some space X, and let's suppose that we have another dynamical system on some space Y. And we would like to give some meaning. Y could be the same space as X, but we'd like to give some meaning to the fact that these 2 points, these 2 dynamical systems, I want to define an equivalence
Can you
relation.
say that there is a map from X to Y such that the thing commute with each other?
Exactly. That's exactly what we're going to do, right? So we would like at least to match up all the periodic points. We also want to match up, in some sense, all the non-periodic orbits. So we're going to say that there exists H. So we're going to say, let me write down the formal definition. So F and G are conjugate, is the correct way to talk about this equivalence relation. If there exists a bijection H from X to Y, such that, what does this bijection? So first of all, there exists a bijection. There should at least exist a bijection. If the 2 spaces are such that you cannot have a bijection between them, you cannot even hope that the dynamical systems are the same, right? So the spaces have to be at least, to some extent, kind of equivalent. And then, what do we really want? We want to say that if we take a point X here, and then this point is going to map to some f of x here, right? Then what is this H going to do? We want H must map x to some x of H, right? Which is Y. And then Y is going to map by G to some point G of Y. Right? And for these orbits, to match orbits to orbits, you really want H to make sure that it maps f of x to G of Y. Right? That's really the property. So we want to find a bijection that maps not just fixed points to fixed points, not just periodic orbits to periodic orbits to make sure that they all match up, but also every non-periodic orbit to some particular non-periodic orbit in a consistent way, which means it needs to send the orbit to the orbit. So if you take a point X, it will map to some point H of X, and then all the points on the orbit also will map to the corresponding points on the orbit here. Okay? So we want this to be equal to H of f of x. Right? So that's the commuting. So we want to say that H, if you apply H, so if you apply f, sorry, what I want to do is I want to apply, this is G of Y is equal to G of H of x, right? Because that's what Y is. So I want G composed with H to be equal to H composed with F. That's what this means exactly. Okay, so G of H of x equals H of f of x. So you can immediately see, so that's just the same thing. So you can immediately see that if x is a fixed point, what can you tell me about H of x?
It's a fixed point.
It has to be a fixed point also. Okay, if this is satisfied. So this condition guarantees necessarily that fixed points are mapped to fixed points. If you think about it a little bit, it also shows that periodic points are mapped to periodic points of the same orbit, so it matches up all the orbits. Okay? So this, in some way, it's telling us that the two systems are in somehow equivalent. So this is an equivalence relation. Can you show me that this is an equivalence relation? So conjugacy is an
In flexibility, we use the identity symmetric H minus 1 and transitive with just compose the H's.
Can we write another form, for example, G is equal to H and H minus?
Yes, because H is a bijection.
Yeah, right.
H is a bijection, so you can write the inverse, right? So that's exactly right. So it's easy to see. So clearly, each map is equivalent to itself because you just take H to be the identity, and then it satisfies this. Clearly, H is symmetric because you just take H minus 1, is also bijection and satisfy the same condition. Okay, I will leave it as an exercise to check. And most importantly, if you have H1 and H2, right, so you have a third system, let me call this F, G, I don't know, L, from some space Z to some space Z, and you can just check, I will leave it to you to check. It's clear that if this is a conjugacy and this is a conjugacy, then this is a bijection, there's a bijection, so you can take the composition, H1 composed with H2, and it gives you a conjugacy between F and L. Okay, so this is an equivalence relation. So this is really an equivalence relation on the space of all maps, just like that. You know, we've defined an equivalence relation. Now we need to check if this equivalence relation is good enough for us, right? The purpose of an equivalence relation is twofold, is to tell you what maps are the same and also to tell you what maps are different, right? And again, you do not want to consider the same maps which obviously are different in some way. You know, you want this equivalence relation to make sense. Okay, we will see lots of examples, but let me say that there are some strengthening of these. There's different levels. So if, let me say again, so if X and Y are topological spaces, and F and G are conjugate, or let's just say, okay, if they are conjugate, and H is a homeomorphism, so remember what a homeomorphism is between two topological spaces? Is a bijection which is continuous and the inverse is continuous. Okay, it's an invertible map that's continuous. So if these two now are topological spaces, and this is actually a homeomorphism between these spaces, then we say that then F and G are topologically conjugate. So this is a stronger equivalence relation, right? If F and G are topologically conjugate, then they are conjugate, right? But they may be conjugate, but not topologically conjugate. You see that? Because this bijection might not be continuous, might not be a homomorphism. Who knows? We will see some examples of this, okay? But it's not, a priori it's not. Is this also an equivalence relation? Yeah, this equivalence relation by exactly the same argument. If this is a homomorphism and this is a homomorphism, the combination, the composition is also homomorphism, and it's a conjugacy in the same way that we've shown before. Okay, so this is another equivalence relation that is stricter than this one. So the equivalence classes are strictly contained inside these equivalence classes. I take all the maps, and you take the equivalence classes by this one, and then you take each equivalence class, each equivalence conjugacy class, and inside, if assuming your spaces are topological spaces, inside you have the topological equivalence class, which might separate more the original equivalence classes. It defines this equivalence classes. What additional structure does this preserve? What properties? So this conjugacy, just in other words, is there a real difference between these two? Are they essentially the same? Can you have, is there something? Omega limits. Thank you, very good. Okay, so notice that if, so this is a, I will leave it as an exercise. It's one of the exercises, there's several exercises. Yes, so exercises. If F and G are topologically conjugate, then if you take X and you look at its omega limit set, this is the omega limit set of X, right? So this is the set of limit points of the orbit of X. And here you have Y, and this somewhere here is the omega limit set of H of X, right? Then H preserves the omega limit set. So H of the omega limit set of F is equal to the omega limit set of H of X. It maps omega limit sets to omega limit sets, which is not necessarily the case for the conjugacy. In other words, this recognizes, for example, if a point is attracting or repelling. If a point is attracting, then the points will converge to it. And if the systems are topologically conjugate, then an attracting fixed point in one system must correspond to an attracting fixed point in the other system, because the omega limit sets, it sees the attracting nature of the point, whereas this one is not clear. It may not do that. Okay? And then we have one even stronger condition, definition. Let's suppose X and Y, let me state it in the one-dimensional setting now, because X equals Y equals R. And then suppose they are F and G are conjugate, and the conjugacy H is a C1 diffeomorphism. Okay, then we say that F and G are C1 conjugate. So what's the difference between a C1 diffeomorphism and a homeomorphism?
C1 diffeomorphism is differentiable and the derivative is bigger than zero always, or not? I mean,
It's never zero. Its derivative is non-zero. It's C1. It's invertible, so it's a bijection. It is a homeomorphism, okay, which is differentiable C1, and its inverse is also C1. Okay, that's what it's C1.
Why it is never zero? Just say that the derivative is continuous, right?
But it has to be bijective.
Because otherwise the inverse would have infinite derivative at that point, which would make it not C1 in its inverse. Right? Part of the definition of a C1 map is that the derivative exists and is continuous and is finite. So that you cannot have a point with infinite derivative is not considered differentiable at that point, actually. So if you have a diffeomorphism that has, if you have a homeomorphism that is differentiable everywhere and has zero derivative here, if you look at the inverse, it will have infinite derivative there. So it's not a C1 diffeomorphism. This is a good, small, subtle point to do with the definition. Okay. Of course, there are situations where you might want to consider maps like this, but they're not called C1 diffeomorphism in that case. So what additional structure does this possess? So this, can you see, so this, is this an equivalence relation? This is also an equivalence relation, because if you have, so this of course does not work just for x and y equals r, but just any interval, and in fact you can generalize this to higher dimension, Euclidean space, differential manifolds, anywhere where you can define the concept of a C1 diffeomorphism between these spaces. C1 diffeomorphism have the property that composition of C1 diffeomorphism is also a C1 diffeomorphism. Okay? So by exactly the same reason we had before, we can compose C1 diffeomorphism and the conjugacy composes, so this is also an equivalence relation. Okay? So this is an even finer equivalence relation, because this says, okay, you look at a class of, an equivalence class of maps that are topologically conjugate, And you say, yes, but which ones of these are actually C1 conjugate? Okay, so for there to be a difference between these conjugacy, this has to preserve more structure than the topological conjugacy. So what structure do you think this preserves? So there is one crucial observation. Huh?
The vector field or
So let me write this. So exercise again. So
sensitive of initial condition.
if P is a fixed point, so suppose F and G are C1 conjugate, and P is a fixed point, Q equals H, so C1 conjugate by some conjugacy H, right? Q is equal to H of P, therefore is also a fixed point, right? Because the conjugacy maps fixed points to fixed point, Q also fixed. Okay, then the derivative at P equals the derivative at Q. So these two fixed points must have the same derivative. This you can easily check just by using this formula and differentiating G and F at the fixed point, and you see that you find out. Okay, exercise to be done. But so this shows that really these are the three fundamental, the three increasingly finer equivalence classes. Okay, you can go further. You can talk about C2, C3, C10, C100, C infinity, analytic, holomorphic. Okay, every level of regularity in the correct setting can be relevant to say this is the level at which these two are equivalent. The stronger the regularity of the conjugacy and the more structure is preserved, and so the stronger the definition of conjugacy is, of equivalence between these two systems is. Okay? So having said that we want to formalize the notion of conjugacy or equivalence, I'm now telling you that there's many different ways, and in many different situations, different ones are relevant. Okay? As we shall see, however, in some sense, the one that really is, in some sense, most significant or most important for most cases, the topological conjugacy. It's the one that, in some sense, reaches the best compromise between being quite strict, but not too strict. Because the C1 conjugacy is very strict. It means that if you have two dynamical systems and they, you can easily show that this also holds for periodic orbits, right? When you take the periodic orbit, if you take the product of the derivatives along the orbit, then it has to be the same for the periodic orbit at P and periodic orbit at Q, right? Not the derivative at the periodic points, but if you take the full orbit, then the accumulated derivative has to be the same. So it really means that the two systems have to be the same in a very strong sense, and it becomes almost impossible for two systems to be C1 conjugate, even though sometimes they are. Okay? So the topological, and on the other hand, when you have just the conjugacy, it tends to give conjugacy between two systems that you don't really want them to be conjugate. Okay? Whereas topological conjugacy really is more or less the correct, in some sense, a very natural form of this. So we're going to, in this course, really try to use this classification to understand certain broad classes of systems. Let me mention just in advance, we're going to do this probably the next lecture, not now, but as soon as you have this equivalence, you can talk about a very interesting concept, which is that of structural stability, which is you can say, okay, take a dynamical system, what if you perturb it a little bit? Does the new system, perturbed system, is it equivalent to the first one, or is it different? Has there been a kind of bifurcation or a dramatic change. Okay, we will see some examples. Rather than giving you more abstract definitions, we will do it in a specific case, but these will be the main themes of the next 5 or 6 lectures. Will be to look at different classes of system, try to understand how we can classify them, and also look at this problem of structural stability, which is about what happens to a system when you perturb it a little bit.
Main problem is how to find the age. It's easy to find age.
Yes, basically the problem is how to find age. Well, to prove that two systems are conjugate, you need to essentially prove that there exists such an age. Age is not usually found explicitly. There are several. I hope to give 3 different constructions here. One is the one of fundamental domains, which is called, I'm going to talk about here. Another one is one called local linearization, and the third one is symbolic dynamics. So in some sense, the main purpose of this course is to give you these 3 techniques for establishing conjugacy between dynamical systems. Okay, and this covers quite a lot of classes of dynamical systems that we can study this way. Okay, so let's try to apply this to, in some sense, the simplest possible dynamical systems. So let's consider Ix, our space will always be the unit interval 0, 1 for the while. Okay? And let's consider the class F or the map F, which are C1 diffeomorphism, C1 diffeomorphism of an interval. So we are going to try to implement a systematic study and try to have some kind of classification of at least most C1 diffeomorphism of the interval. Okay. So what does a C1 diffeomorphism of the interval look like? So we have a map I from 0, 1 to 0, 1, right? So we can draw the graph. That's the advantage of working in 1 dimensions. It's easy to draw the graph. Okay. So what can you tell me about the graph of a C1 diffeomorphism?
Well, it's continuous, so it has a maximum, and the derivative is never 0, so it's either positive or negative, so
yes.
It's either increasing or decreasing.
It's either increasing or decreasing. This is going to be something that we're going to use in a fundamental way. The derivative is always either positive or always negative. Yes? Also, it's a bijection. Right? It's a bijection. So for it to be a bijection and not to have 0 derivative, what can happen? If the image of 0 is here, okay, then how can it, and from here, it cannot be constant because otherwise it's not a bijection. It's not invertible, okay, it cannot work. So from here, it needs to go either up or down. Okay, so it cannot be constant. So if it goes up, as you said, it can never have a 0 derivative, so it can never come back down again. Right? So it can do something like this, but this is not a bijection. Why is it not a bijection? Yeah, there's no point that maps to here. Right? It needs to be surjective, so it needs to map to everything. So this implies that this image of 0 cannot sit anywhere in the middle of this interval.
So f of 0 is 1 or 0?
Exactly. So f of 0 can be 0, right? And if f of 0 is 0, then this must be increasing, and f of 1 must be 1 for the same reason, right? So it needs to be something like this. Or it could also be 1. So f of 0 can be 1, and f of 1 can be 0, and then it would be something like this.
At most 1 piece, and 1 piece is 1.
So, if it's so, we say that F. So what are the properties that we know? First of all, endpoints map to endpoints. Right? 0, 1 maps to 0, 1. So F of 0, 1 also is equal to set 0, 1. Yes. F prime of x is always different from 0 for all x, otherwise it's not C1 diffeomorphism like we just said. Yes. For all x in I. Contradict, otherwise not C1 diffeom. So either f prime of x is positive for all x, or f prime of x is negative for all x, and this, in this case, we call this orientation preserving. And in this case, we call it orientation reversal. And why do we call it orientation preserving, orientation reversing? Because if you take 2 points x, y, where y is bigger than x, and you look at the images are reversed, right, in terms of equality. So here, in this case, you definitely have, these are monotone, right? Because the derivative is never 0, in this case, the derivative is always negative, which means the graph is monotonically decreasing, which means that in this case, we have that if x is less than y, this implies that f of x is bigger than f of y, right? And orientation preserving means that if x is less than y, then this means that f of x is less than f of y. This would be a property that will play, which is basically the reason why these are very simple to study. Okay, they're called monotone maps, and this will simplify very much what we want to do. Okay, so fixed points. That's right, fixed points. So in the orientation reversing case, there can only be one fixed point. Why is that?
In which case?
In this one, in the orientation reversing case.
Yes, because it intersects y equal x.
Because a fixed point is where the graph intersects the diagonal.
Yeah.
And in this case, it can only intersect the diagonal in one point. Right? Because it is monotonically going from left to right and it cannot come back on itself. Okay? So in the orientation reversing case, is only one fixed point. And what about in the orientation preserving case?
Only two.
No,
No,
because
okay,
they
finite.
their identities also.
Only two or all of them?
So certainly 0 and 1 are fixed points, so at least 2. Okay? But then we can have many. We can even have infinitely many.
But it would have now the derivative 0 at this point. At that point.
No, derivative 1 perhaps. Derivative 1 maybe because it's going up. Yes. Yes. So orientation preserving has at least 2 fixed points. So if the map is orientation reversing, what can you tell me about the second iterate of the map?
It's now orientation preserving.
It's now orientation preserving, right? Because the second iterate of the map is equal to f composed with f, right? And what's the derivative? The derivative of some point on the second iterate by the chain rule is the derivative in f of x times the derivative in x. You recognize this as a chain rule? I haven't actually talked specifically about the chain rule, but it's something we're going to use a lot, so I will talk about it a lot. Remember the chain rule, if you take a composition of two maps, then the derivative of the composition is equal to the derivative of one map times the derivative of the other map image of the first map. In this case, they happen to be the same map that you're composing. So because it's orientation reversing, each derivative is always negative, so the product of the two is positive, okay, for any 2 points. So F2 will always have positive derivative everywhere. So it's orientation preserving. Okay, so this is orientation reversing, implies that F2 is orientation preserving. Which means, so you can see that it may have lots of periodic points of period 2, right? If this is orientation reversing, so it has one fixed point, but 0 is a periodic point, right? Because 0 maps to 1, 1 maps to 0, so it's a periodic point of period 2. And 1 is also a periodic point, they're the same orbit. And then you might have other periodic points, right? So you might have, it might be that you have this point here, x, maybe maps to here, like this is f of x. And then, where is f of x? F of x is somewhere here. This is f of x, okay? And maybe this maps, okay, the drawing did not come out exactly right, but maybe f of x maps to x itself, so you might have a periodic point of period 2. Okay? So in the orientation reversing case, just like you can only have one fixed point, but you may have many periodic points of period 2, and you would see those periodic points when you take the second iterate of the map, because you actually get an orientation. If you take the graph of the second iterate, you will get where these two fixed points are, where these two periodic points are, you would get a periodic point, okay, and maybe some other points here, in which case you'd have to have them here as well, okay? So it's more difficult to see the picture of what goes on in this orientation reversing case, but in terms of the theory, we really only need to study the orientation preserving case, because if you take any orientation reversing, you take the second iterate, and then everything that works for orientation preserving case applies to the second iterate, okay? So from now on, we're going to concentrate on orientation preserving interval diffeomorphism.
But by taking the second iteration, we also lose some information about the dynamical system.
Very little. Only the fact that it's every fixed point is a periodic point of period 2. Very little information, yeah, in this case. If you had to be taking many different iterates at different times, you might be more. But this is really just the second iterate of the map. So you can pretty much go back. If you prove anything about F2, you can pretty much go back and see what that means for the original map, yes. So in this case, there's not really any real loss. Okay, so what we would like to do is classify, okay, so let's try to classify orientation preserving C1 interval diffeomorphism. Okay. What does it mean, classify? Yeah, we want up to topological conjugacy, right? That's what, or up to these various kinds of conjugacy. So we want to see if different interval diffeomorphisms, for example, we take, let me do an interval diffeomorphism here. So we know, let's start always with the simplest case. So the simplest case, as you know, as we've said before, one of the first things is the number of fixed points. Any notion of equivalence will have to preserve at least the number of fixed points. So let's look at the simplest possibility, okay, which is that we have just two fixed points, 0 and 1, which means that the map does something like this. Okay, this is F. Or it may do something like this.
Concave or convex?
Sorry?
Concave or convex?
Yeah, not necessarily along the lines, but more or less, yes, more or less. It's either above the diagonal or below the diagonal. Okay? So my question will be, which ones, so here, suppose we have another one. So here we have one, our starting map F, and then here we have one that is below the diagonal, here we have one that is above the diagonal, but maybe quite different, like this, for example.
But it can also cross the diagonal, right?
We are going to suppose we only have two fixed points for the moment, right? Because we know that if this one crosses the diagonal another point, it cannot be equivalent conjugate to that one, because it has different number of fixed points. Okay? So later we're going to generalize to an arbitrary number of fixed points, but for the moment to study the problem, let's restrict. Okay, so initially, suppose first that there exists exactly two fixed points. So whatever kind of classification we have, restricted to this, it will have to make sense, because if we take more fixed points, they will be in different conjugacy classes. So there's nothing we can do.
But in this class we have just one structure, yes? Every two map is topological.
That's what we're going to discuss. That's what we want to establish, right? So we need to do two things. First of all, we need to show. So what is your guess about this? Are you saying that you think these two are topologically conjugate?
Yes.
Are they C1 conjugate?
I don't know what topological conjugate by lines is.
What about these two?
Topological conjugate?
Topological conjugate? Okay, let's see what we can do. Yeah? So let's construct a topological conjugacy. Yeah. Okay, so we're going to show, in fact, yes, these are all topologically conjugate, so that's correct. And I want to show you, let's look at these two cases. Okay, we would like to construct a topological conjugacy. So there's various steps we're going to do. So first of all, let's get the topological conjugacy has to preserve omega limits, right? So what are the omega limits of the points in here? What do you think are the omega limits? If I take a point here.
The fixed points.
Sorry?
The fixed points.
That's right. Could it be anything else?
We have two cases, 0 or 1. It's because 0 and 1 are attractive sources.
But how do we know that the omega limits of x has to be either 0 or 1?
They are
Because
continuous.
if f of x is bigger than x, so in this case, every iteration is bigger than, and we have just a monotone sequence, and it has limit in this case, and the limit is fixed point, so.
Exactly, but this is a set of non-trivial observations you just put together, right? Some of them that we did before. So this is going to be one first exercise, which is already in the text already exercise. If f is a C1 diffeom, okay, then for all x in I, the omega limit set of x and alpha limit set of x are fixed points. Okay, it is relatively elementary, but it's not completely trivial. You need to say exactly what he said, which is that the sequence is. So let's look at first of all, just graphically. There's a kind of trick to get a feeling for what's going on here. So remember, first of all, let me illustrate. Use this problem to illustrate a graphical technique that is very useful here. And for this, you need to keep in mind something that is very important, that this is the graph of the map, okay? But what is the space on which the dynamics is actually taking place? Below, exactly, right? So remember The map is a map from 0, 1 to 0, 1, which is this. So it's very important because this can create a lot of confusion initially, okay? This is just a graph, so the dynamics is not taken, this is not a two-dimensional space on which points are moving. The points are moving on this space, but the graph can be very useful to get a feeling for what's going on. Why? Because if we take x here, right, then the graph tells us that this is f of x. Because this is a copy of the unit interval. Okay? But this does not mean that this map maps this point to this point. What point does the map f of x to?
From the base point.
Exactly. It maps f of x here, and there is a nice graphical method to find out where f of x is here. Because now that we have it here, we can go and look at the diagonal, and we can find f of x. Yeah. So we can find here where f of x is here, and then we can do it again. We can take f of x, and we go up to the graph, right? And this is now f2 of x. Okay. Now we do the same thing. Remember, the dynamics is actually happening here. So now we go across the diagonal, and we come down, and we find f2 of x. Yes. And then when we get a little bit good for that, we don't need to keep going back and forth here, right? So now we've got f2 of x. We just go here. Now there's no point in going all the way here and all the way back. I just go across to the diagonal. And then there's no point really coming all the way down and then going up again. I just go up to the graph again, across to the diagonal, up to the graph, across to the diagonal, and it looks like things are moving towards this. This is sometimes called a web diagram. I can't remember, there's a name for that, a kind of called web diagram, okay? So this, however, is not a proof. So if you look at the sequence, so this sequence, this is giving you a sequence here, right? So this is f3 of x, and so on. So this is looking like it's giving you a corresponding sequence of points that's converging to 1. So when you just look at this, it can be very useful, and you say, oh yeah, you know, it's clearly, it's converging to 1. So the sequence of it is converging 1. But you need to prove that, right? And the proof that is exactly what he said, which is that because this map is orientation, is monotone, which means that each image is bigger than, each point, its image is bigger than the previous one because the derivative is bigger than 0. So you take the sequence of the orbit is monotone, right? So the orbit is monotonically increasing because each one is bigger than the one before, but it is bounded. And therefore, any monotonically increasing sequence, bounded sequence, converges. Okay, that's just it. There's no other dynamics. You've used the dynamics to create the sequence, and then it's just a fact from topology, from analysis, whatever. It's a monotone sequence and it's bounded clearly because this is a map from 0, 1 to 0, 1, so it can never go beyond 0, 1. So this is always bounded. Okay, bounded. It's always less than or equal to 1, so it must converge. And by the exercise that we did before, if you have an orbit that converges to a single point, then that point must be a fixed point. Remember? So if you have the omega limit as a single point, then it needs to be a fixed point. Okay? So together, putting together these observations, which you should write down to make sure you understand, then it follows that the omega limit has to be a fixed point. You can do exactly the same argument for the alpha limit because then it's monotone decreasing. It's exactly the same thing. And since there's only two fixed points, then this means that the limit must be, the alpha limit must be 0 and the omega limit must be 1. Any questions? Okay. So both of these have the same property, right? So there's the same thing here. This is also monotone increasing. So here also, if you take a point y, then it will converge to 1. And the alpha limit will be 0, right? Because these points will be 0. So if you take, so the first observation we're making is that if you take a C1, two in C1 interval diffeomorphism with exactly two fixed points, then every point has its alpha limit is 0 and its omega limit is 1. Right? So that's the first clear observation statement that we make about what they have in common. This does not automatically give us the topological conjugacy, right? But it is pointing in the right direction. So what is the thing we certainly will need? What will have to be the image? So we try to construct H. What we know is that it must map 0 to what? To 0. And it must map 1 to 1 because it must map fixed point to fixed points. But why can it not map 0 to 1 and 1 to 0? Why can this homomorphism itself be orientation reversing?
Because of this differential, the differentiation must be the same at fixed points for C1 diffeomorphism.
No, we do not try H to be a C1, so don't confuse the fact that now our maps are C1 diffeomorphism. But our conjugacy, we only want it to be topological, right? So if H was C1, then it would have to map C1 to C1. But this brings us to the reason why in general this cannot be C1, right? Because H must map 0 to 0, at least the fixed points to the fixed points, if the derivative at this fixed point is different from the derivative here, this automatically shows that they cannot be C1 conjugate. Okay? So this already shows you how strong the C1 conjugacy is, right? So you may have, we're going to show that all maps that have basically this picture, they're all topologically conjugate, but inside this there's an uncountable number of C1 equivalence classes because every different possible value of the derivative here will put them into a different C1 equivalent conjugacy class. Okay?
Just at the fixed points or at the endpoints or just at any point?
At the fixed points and the periodic orbits. It gives a restriction, a priori at least that's all we've showed for the moment, is that the derivative, we will see in the construction that if they have the same derivative as 0 and 1, you can make it C1, this conjugacy.
Sorry?
If they do have the same derivative, we will be able to construct the C1 conjugacy. So in this particular case, in fact, if they do have the same derivative, they are also C1 conjugate. It's a stronger statement and it requires stronger assumptions from the maps. So why can we not send 0 to 1 and 1 to 0?
Because it converts the dynamics to only one fixed point.
No, this is just H. This is a homomorphism. It needs to map fixed point to fixed point, here and here. And I know that we've got two fixed points here and two fixed points there. So how do I know that I want to map 0 to 0 and not 0 to 1 and 1 to 0?
Because of continuity.
Continuity of what?
There should be H is continuous function.
That's okay. You can have a orientation reversing map from 0, 1 to 0, 1.
In this case, we have orientation reversing.
Can we obtain orientation reversing?
The homomorphisms can be orientation reversing. We did not put any restriction on that. The definition is that H is a homomorphism that conjugates the dynamics. But what structure did we say that it preserves compared to a normal conjugacy? We said it preserves some structure. Remember, there were three. The conjugacy preserves fixed and periodic orbits.
Limit points.
Exactly. The topological conjugacy preserves omega and alpha limits. So,
In this case, they are different than.
right? So in this case, it means that since x has 1 as an omega limit, then whatever I map the map x to, y is equal to h over x, it must map, its omega limit must be the image of the omega limit set of x. It must map omega limits to omega limits. Since x has its omega limit 1, every point here has its omega limit 1, every point here has its omega limit 1, so whatever homomorphism we construct, it has to map 1 to 1, okay? Because it has to map omega limits to omega limits.
So
Is that clear?
Does it map omega limits to the image of omega limits, or
So remember the definition. So if H is a topological conjugacy, then the image of the omega limit set of some point x, so you take x, it has an omega limit. The image of the omega limit must be the omega limit of the image of x. In other words, the conjugacy maps H to some point here, which we don't know what point it is, okay?
Yeah,
But it must take the omega limit of x to the omega limit of the image of x.
okay, so what's the problem if the images get mapped to the
1, 0 to 1.
To the opposite images. Because x, the omega limit set of x is 1.
okay.
And the omega limit set of y is also 1.
I see, okay.
So we must map 1 to 1. If our homomorphism was orientation reversing and mapped 0 to 1, then it would map the omega limit set of x to the alpha limit set of h of x. Okay? Yeah? So since omega limit set of x is equal to 1 for all x, and the omega limit set of y is equal to 1 for all y under G, right? Omega set limit set under F and omega limit set under G, we must have h of 0 equals 0 and h of 1 equals 1. So we're slowly building up the construction of this homomorphism, right? Step by step. So the first thing we observe is that.
In general, this homomorphism is not necessarily unique, right?
It's not necessarily
Unique. It's far from unique.
This is not unique, but this is going to depend on a choice that we're going to make. What's unique is this property. We know that it maps 0, 1 to 0, 1. But now, the next step of the construction, which is fundamental, is going to show that there's many, many different choices. And the strategy is the following. It's going to use the concept of a fundamental domain. So let me write the definition. So let's say, write the definition in a very abstract setting. We have f of x to x. Okay, set A in x is a fundamental domain for f on x if for all points x in x there exists unique tau in z such that f tau of x belongs to A. So in the abstract setting, this is our space X. Okay, now we're saying that there exists a set A. So what is the statement saying?
Any point eventually enters A.
Not only that, it enters A, and then what does it do when it's inside A?
Stay.
No, it doesn't stay. It immediately leaves because there's only one moment. So every point eventually enters A, but every point in A leaves A immediately and never comes back. So if you look at the full forward and backward orbit of the point, it only lands once and only once inside A. This also means, what does it say about the images and pre-images of the set A? So if now you take f of A, intersection A,
empty.
What about this intersection? Is it empty or non-empty? Sorry? It's empty. Why?
Since every point comes in once.
Exactly.
Then we apply it before.
Exactly. It means that every point of A must leave A. Okay? And the same if you put F2 of A.
Yes.
Okay? And the same if you put Fn of A. And in fact, it's easy to see that all of these are all disjoint. Okay? So this implies if there exists a fundamental domain, okay, this implies that all the iterates Fn of A and in Z are pairwise disjoint.
They form an equivalence class of X.
Excuse me?
They form an equivalence class of X.
They form a partition.
Yes, a partition.
They form a partition. Equivalence classes also form a partition, but here there's not really concept of an equivalence. They form a partition. In other words, if you take A, F of A, so all of these must all be disjoint, and the union must be A, because must be all of X, because every point falls inside A once. So every point has the orbit that belongs to A. Okay, so it means that if you take A and you look at all its forward and backward image, you reach every point of X belongs to some image of A. Okay, so this looks like a very, a priori looks like a very strong structure, but actually it's very easy to find some fundamental domains in here. How do we find a fundamental domain for this map, for example? Is the whole interval, is it a fundamental domain if we take the whole space?
Open interval, of course.
The whole space is not, because
Yes.
because the point stays inside it for all time. Okay?
Oh. Just zero.
Just zero has the property that everything converges to zero in forward time, but nothing lands on zero, except zero itself, so you do not fall inside. Okay?
So, what's the question again?
To find a fundamental domain here for 0, 1 in this space, for this map. So you see, this is the difference between abstract definitions and a concrete example. Right? So the abstract definition, okay, it's like this. So you want every orbit to fall once and only once inside A, all the other points. Or you can look at it two ways. These are two equivalent ways to look at it. One is to say that these are all pairwise disjoint and the union is all of X. Or you can say it like this. They're exactly equivalent ways of saying it.
But in such partition, is it used from such a fundamental domain?
No, not necessarily. Well, yes. If you have a set with this property, then any element of the set is can be used as a fundamental domain, right? Because these are all images of some set. So if you take A, this means that all the others are disjoint, but this means that every point in one of these, either in backward time or in forward time, will fall in A once. So these two are completely equivalent state, just ways of seeing the same situation. Yes. So the question is, let's find a fundamental domain here. Well, the good thing is that you know that points, what do points do in backward? Take this point Y. Where does it come from in backward time?
0.
It comes from 0. So in backward time it goes to 0. Okay? And where does it go in forward time?
1.
To 1. Okay, and that's true for every point. So all the points, what they're doing, in some senses, they're going between 0 and 1. Right? So the situation is promising for a fundamental domain, because you just want to kind of take a little interval here and make sure that every point, as it moves here, it must jump in here once and then jump out and then go to 1. I mean, it's not a complicated situation where points are coming back to each other all the time. Here, once a point leaves someplace, it never comes back. It just goes towards 1. And in backward time also, it just goes towards 0. So we want to define some kind of interval here that we are sure that every point, if you start, suppose you now start with a point here, make sure that you fall inside.
Yes, so f of x would be bigger than the length of the interval plus the point.
Actually, it depends on derivative of the function.
Yes. So,
You're making it more complicated than
because
it
we
is.
need to know the difference between f of x and x.
Well, you need to know it, or you can just say f of x and x. So let's, well, I'm calling it y. Let me call this y. And let me call, this is g of y. Let me define an interval like this, for example. And let me take it open on this side and closed on this side. Okay, so the interval y, g of y. So, does it, first of all, does it have the property that all the points in here, they leave after one iteration? Yes, right? Because of the monotonicity, the order preserving, right? So if you take the point y maps to g of y, and every point that is to the right of y, it must map to the right of g of y. And then it must continue towards 1, so it never comes back. Again, yes. So we already have this, that in forward time, we have this property, right? And if we take the image, well, if we take a point in A, it never comes back. And how do we guarantee that every point on this side, it lands in here at some point?
Because we take all the iterates of it and we take the last one before y. And this last one must be mapped inside this interval.
And why can it not jump over?
Because that also contradicts
Yes. Yes. Okay? Because if you take a point to the left of y, its image will be to the left of g of y. Every point that starts to the left of y, its image must be to the left of g of y. But every point is eventually coming here. Okay? So every point, it gets closer and closer and closer. And then however close it gets to here, it's always to the left of y. And then its image must be to the left of g of y. So before it can jump to the other side, it must have one iterate in here. Okay? So let me know if you want me to formalize these arguments, right? Better if you want me to write down the formula. I mean, I think it's, if I explain to you exactly the argument, of course, the exercises you should always do is you should make sure you can write formally these arguments. Right? This is an important exercise to do. But the statement, if you want the lemma, which you can prove as an exercise, is that for every y in 0, 1, so except for 0, 1, in the open interval 0, 1, this is a fundamental domain for f on 0, 1, and the whole interval 0, 1. Okay? So there's many fundamental domains because we can choose an arbitrary, any arbitrary point here. Y, we take g of y, that's a fundamental domain. This is A. So what's the point of having a fundamental domain? What's it good for? So, again, I'm going to first draw it in an abstract setting. So suppose you have two fundamental domains. So let's suppose we have f x to x, and then you have a fundamental domain A, and then suppose we have g y to y, and then you have some fundamental domain B. Okay, so AB fundamental domains. So I'm going to start by trying to construct a conjugacy between the two. Let's forget about the topological or C1 structure, just a conjugacy, bijection. How do we construct, how do we use this information to construct a conjugacy? Remember, the conjugacy is a bijection between these spaces which maps orbits to orbits.
It only suffice to map to do it on the level of fundamental domains.
Yeah. Why? Because suppose I can define a bijection between A and B. Okay, so let H0 be a bijection. Any bijection.
Because we now know the future and the past of any point, and we can use this compatibility condition to determine which one would be mapped to.
Exactly. Because if you remember, the concept of a conjugacy is that it matches orbits to orbits. Right? And in some sense, the points of A, they index every orbit. Every orbit in the system has exactly one point in A. Remember, yeah? That's how we did it. Every point just falls at one in A. And every orbit in the system has exactly one point in B. Okay? So as soon as we have a bijection from A to B, morally, we still have to do some steps to get the conjugacy, but morally, we have matched up every orbit to itself, right, in whichever way. We've said this point associates to this point, and so in some sense, this point represents a full orbit in the system, and this point represents a full orbit in the system, so we're matching up all the orbits in the system here to all the orbits in the system. Okay, for any bijection. Now we need to write this down formally. Okay, what does it mean? So we need to construct a, we need to say, okay, where is this point? So now we take a point here, and we want to construct, we're trying to construct this conjugacy, this bijection on the whole space. We have a bijection on A and B, so what do you suggest? Now we want to know what the image of, we want to figure out what point H is going to map this
Find the
point.
tau in which f of tau of x is inside A, and then we take the image of this point, and then we trace back
Exactly.
by minus tau.
Exactly. Yes, okay. So by definition, this point falls in A at an exact time. Okay, so let x belong to x, okay, and let tau of x is the unique integer such that f tau of x belongs to F. Okay, so this could be positive or negative, right? We don't know. But so that at some point, this f tau of x, this is tau that depends on x, so you've chosen a point and you have a certain point here. Now this maps to some point here, right? So now here we can look at this point here is H0 because we have a bijection H0. H0 of f tau x of x. This is the point that is mapped. And now what do we do to this point? And now we define another point here. So let y is equal to, what do we do with this point? We iterate backwards by g minus tau of x. I mean backwards or forwards, minus tau. So if tau was negative, we iterate forward. If tau is positive, we iterate backwards. So this is equal to f minus tau x of h0 of f tau x of x.
G or
Sorry, g, yes. Thank you. Y is equal to g of minus tau x, h0 of f tau x of x. So the question is, does this define a conjugacy? Yes, this defines a conjugacy. We literally have this formula right here, right? So, we now have a new map. So okay, so what I really wanted to say is let H, okay, what I wanted to say is let H of X to be by definition this map. Sorry, I didn't mean Y. So we choose any point X here, and this defines a point H of X. Okay, in this way. So I will leave it as an exercise to check. Okay, that H is a bijection, okay, and a conjugacy. But it's quite easy to see that it's a bijection, right? Because it's everything is completely symmetric. So every point in here gives you another point here, but every point in here gives you a point here. So you can see that it's a bijection, and because of this formula, you can just see that it gives you a conjugacy between these two things. Okay? This is just a conjugacy. It's not yet a topological conjugacy. There's no structure here. But let's, to see it's a topological conjugacy, we need a little bit more information. You cannot do it in abstract here. So let's look at this case, right? So how are we going to apply to this map here? We're going to construct a conjugacy between these two maps. So we have constructed a fundamental domain here, and we construct another fundamental domain here.
There is an easy map of straight line between two intervals.
We can use that, for example. Then there's many, as you see in this exactly, there's many choices, as you say. There's two places in particular where we don't have uniqueness, it's not canonical. One is the choice of A and B, because you can choose A or you can take the image of A. Any of these images of A can be used as the fundamental domain, right? And the same for the image of B. And then once you've chose this, there's bijection. Any bijection you can use will work, at least as far as the conjugacy is concerned. Okay. So in this case, we take any arbitrary point X, and we take the open interval here, f of X. Right. So here we take the set A is this, the set B is equal to X, f of X, open interval. And then all we need to get a conjugacy is a bijection between A and B. Yeah. So this can even just be affine. It can be linear. It can be affine. You know, it can just be take the length of this and just stretch it uniformly or contract it to get the length of A, and then just map it here. So clearly, there's many different ways in which we can do this bijection. And what about the homomorphism? So can we construct? So in this case, so we can use this. Use this to construct conjugacy between the two interval differs. So we have something, okay, so we have to construct a conjugacy H, 0, 1 to 0, 1. And how do we know if this conjugacy is continuous, is a homomorphism? In this case.
You can define it to be any.
So first of all, we make sure that the bijection we choose here is a homomorphism. Okay? So show H is a homomorphism. So we already know that it's a conjugacy, right, by construction. So all we need to show is that it's continuous and the inverse is continuous. We know it's invertible because it's a bijection, we've got a conjugacy, okay? But a priori it might not be homeomorphic. For example, the bijection we've chosen from here to here might not be continuous, might not be homomorphism, right? So H restricted to this, so what does H do? H takes every point of this whole interval to every point of this whole interval, right? It maps B to A according to H0, which is what we've chosen. So here we have H0. So the first thing you need to make sure is that H0 is a homomorphism. Of course, otherwise you've got no chance, okay? So make sure you've chosen, but this is up to us, we can easily show, make sure it's a homeomorphism. Okay? And then how do I show, for example, so what does continuity mean? Continuity, remember, is a pointwise condition, right? So we want to show that H is continuous at this point here. How do we show that it's continuous at that point?
Probably it's an image, and take a neighborhood around the image.
Okay, yes, you all have different things. So,
Is it contained in an interval or is the endpoint?
so what information do we have? H is a composition of three maps. Right? Remember,
The inverse
so
image of
H of X is equal to the composition of, we start with F tau X of X, then we compose with H0, and then we compose with G minus tau X. It's the composition of the thing, okay? So if this is going to be continuous, it's enough to show that each of these is continuous in the corresponding point, right? So we can look at it like that.
But also we need to check at the endpoints.
The endpoints are the most difficult ones, yes. So let's check. So how do we show? So suppose that this, after some point, lands in the interior. Yes, so this is easy. Why is it easy? Because we know that F tau of X is always continuous, because F is a C1 diffeomorphism. So iterate tau is a C1 map, right? So this part is C1. Okay? The difficult part, both of these, both F and G are C1, so the iterates of F is C1, the iterates of G is C1. The problem in some sense is H0. Okay? So if we fall inside in the interior here, then it's no problem, because this is C1 from here to here, it's C1. You have a little neighborhood that maps to a little neighborhood here. Everything is nicely C1 here. And then from here to here, you have homeomorphism, because you've just decided it's a homeomorphism. And then from here to wherever it was, you go back and you apply this, which is diffeomorphism. And so H is continuous. So H is continuous for all. I'm using, maybe I should use a different notation here. Let me use Z here, because I've used X and F of X for this. So this is Z. So H is continuous for all Z such that F tau Z of Z falls inside the interior, okay, falls inside the open interval X F of X, right? So this is the interior of the fundamental domain. Is that okay? So if you take a point here that falls in the interior, then you just compose these things, okay? So the problem lies here. And at all the images and pre-images of this boundary point. It's a little bit less trivial. So how do we show continuity of the map H there? How do we show continuity at this point? Well, continuity has continuity from the left, from the right, and from the left, right, to show that a function is continuous. So here, for points here, then the tau is 0, right? So in this case, it's just H0 is the map, right? Because if you start inside the point, inside the fundamental domain B, then all you do is you apply by H0, okay? H0 is a homomorphism, so from the right, it's continuous by definition, because we've chosen it as a homomorphism. The problem is continuity from the left.
This is f inverse of x and x. This is the same. It's continuous there.
Exactly, right? So we take what is the image. So you need to take a sequence. You need to take a sequence of points to show continuity from the left. This is really very hands-on. Epsilon delta, right? So you take a point very close on the left to x, and you need to show that its image is going to be very close to the image of x. Is that true? What is the definition here of the map? If you take a pen that is very close to x, then what is going to be the tau of z? If you take a point here,
It would be very close.
1. Yeah, because after 1 iter, it falls in here. Yes? And so if tau is 1, you apply tau equals 1, it falls in here, and then you apply H0, and then you apply minus tau, which is minus 1, and so where it's going to end up? It's going to end up very close to this endpoint, right? The closer you get to here, and the closer it's going to come to g of y under H0, because you've got a homomorphism in here. Sorry, the closer you get to here, and the closer it's going to be to f of x, it's going to land in the interior. And then because this is a homomorphism onto its image, it's going to be very close to g of y, and therefore its preimage is going to be very close to y. Epsilon delta, literally definition, right? So you show that if you take that there exists a delta such that if you're sufficiently delta close to here, then its image will be epsilon close to that. I will put this question in the exam. Okay? You must know. This is a little technical detail, but you must really make sure you know how to formalize this continuity, okay? Because it is crucial that you show that this conjugacy is a topological conjugacy, and for it to be a topological conjugacy, it does not follow just from the abstract fundamental domain arguments. So the abstract fundamental domain argument says you just take two fundamental domains, you take a bijection that gives you a conjugacy in the two spaces automatically, okay? But if you want this conjugacy to be a homomorphism, you need to use more information about the systems. Like in this particular case, we have a lot of information about how these fundamental domains match up at the boundaries, okay? And we use that to show that you have continuity at the interior and at the boundary, which is the key point. And you show that so we've just shown that H is continuous everywhere, okay? And then the argument to show that H minus 1 is continuous everywhere is completely symmetric, because this definition works completely exactly the same when this operates. Right? So you show that H is continuous at every point, H minus 1 is continuous at every point, and you get the topological conjugacy. And how do we know that we cannot, in general, make this conjugacy differentiable? Because I could perhaps do something about the differentiability here. If I took H0 to be C1, to be a diffeomorphism between here and here, which I can do, okay, then why can I not use a similar argument to get differentiability at all these points?
F and G itself may not be C1.
No, F and G are C1. F and G are C1 diffeomorphism, we've assumed, okay? And in the construction, since I'm dealing with intervals, I take a bijection H0 here, between this and this. I can just take a C1, I can even take it kind of affine, okay? But, and I still get, for the first part, for all the points that lie in the interior, then this is C1 at all those points, okay? But how do we know that unfortunately this last part of the argument is not going to work?
Maybe the continuity of the derivative from left and right do not coincide.
How do I know that there's no way I can make it work?
How do I know?
Like finding the lambda.
Because I told you that if you have a C1 conjugacy, it preserves a certain structure in the map.
Yes, the derivative.
The derivatives at the fixed point. So if the derivative at 0 and here at 0 are different, then there's no way it can work. Okay, I'm not saying that I cannot do it because I don't know how to do it. I'm saying that I cannot do it because I know for sure I cannot do it, because it would contradict the fact that a C1 conjugacy preserves the derivative at the fixed points. If the derivative is the same at the fixed points, then you can try to see if you can show that if the derivatives are the same here, then you can work it. I'm not exactly sure if you can do it by hand, to be honest. I think so, but I'm not sure. But certainly if the derivatives are different, then you cannot make this construction. You can make this construction a homomorphism, but not a diffeomorphism because of that obstruction. Okay? So this is it. This is the first technique that I was telling you about, fundamental domains. We're going to use it also in a slightly more general setting. But it's a very interesting technique, it's a very important technique, and it's a very easy and natural technique to show that two systems are topologically conjugate. We don't have time now, but of course this is just in the special case in which we have two fixed points, right? So tomorrow, or the next class, we will look at the general case and look at some other possibilities. Okay? Thank you very much.